Hello, Professor Sargent here with you again for another Math 101 flipped classroom lesson. In section 3.1, we talked about solving 2x2 linear systems of equations. We used graphing, substitution, and elimination. Now we're going to look at 3x3 systems of linear equations, meaning that we will have three equations with three variables. We're not going to be able to graph these in some advanced mathematics classes, at least back when I was in college, we did. But what you would wind up graphing instead of a line is a plane. And let's see here. I want to point out that there are still overall three possibilities. Either one solution where all three planes intersect at a single point, or you could have no solutions or infinitely many solutions, although things get a little interesting with those last two special cases. And they show that here on the first page of the section. A single solution, or you could have two walls and then a piece of paper. Let's say you have your walls meeting right here, and then a piece of paper coming in at an angle like that. They would be intersecting at a line, so infinitely many solutions. You could have parallel planes, or two parallel planes and one slicing through them, etc., etc., etc. Still, this is all boiling down to those three cases: one solution, zero solutions, or infinitely many solutions. The key to solving the 2x2 linear systems when we used either substitution or elimination was to come up with, from a 2x2 system, come up with a 1x1 system, meaning one equation with one variable. Once we knew the value of that first variable, we could go back and solve for the other. So in the case of a 3x3 system, we want to go from 3x3 to 2x2 first of all, because then we'll be back on familiar ground. Once we can go to 2x2, we can go to 1x1. Notice in this first example that the first two equations have y, but the third one does not. What I'm going to do is pick the first pair, equation 1 and equation 2, and eliminate x. Okay, I've multiplied everything in equation 2, each term on both sides, by -5, and now I can get the x's with that new version of equation 2 and the x with what we have in equation 1 to cancel out. And here's what I get when I add along the columns for all those like terms. What good does that do? Well, now, besides equation 3 being an equation just involving y and z, I now have a fourth equation involving just y and z. And I could either multiply everything in equation 3 by 5, because 25y would cancel -25y, or I could multiply everything in equation 3 by 3, because a -3z would cancel +3z. I'm going to go with that smaller number. I'm going to multiply everything in equation 3 by 3. Here's what I get when I multiply everything in equation 3 by, equation 3 by 3. And now I'm going to add it to that new equation, equation 4. Not only do I add up these z's to cancel them out, but I also add up along the y column and along the constant column. I get -10y equals 10, divide both sides by 10, and y equals positive 1. Divide both sides by a negative 10. Furthermore, now that I know that y is 1, there was one equation that had only one other variable. Equation 3 only had z in it. So now I can solve for z. I'm going to multiply the 5 times 1, combine the like terms, and divide by negative 1. By doing that, I find that z is also equal to positive 1. Now I'm going to look for an equation back in the original 3 that had both y and z, but also has x, so that I can solve for x. I could use either equation 1 or equation 2 to do that, but equation 2 just has a coefficient of positive 1 in front of x. And also putting in 1 for y and z is going to make this nice. Combine the like terms that are on the same side with that same operation of addition. X plus 5 equals 7. And then subtract 5 from both sides because the 7 and the 5 are on opposite sides. We're going to get that x equals 2. You may be asked to write this as an ordered triple. Just like with 2 by 2 systems, we had the XY ordered pairs. Now we would have an XYZ ordered triple. And so it would look like this. And also it would be a good idea to go back to your original 3 equations, plug in 2 for x, 1 for y, and 1 for z. For example, 5 times 2 is 10. Minus 5 times 1 is 5. So 10 minus 5 is 5. Z was 1. So 8 times 1 is 8. 5 plus 8 is 13. It'd be a good idea to check that in all 3 equations. Now, in our second example, this is not as nice because we don't have an equation that just has 2 variables. So now, let's look at what would be something that we could cancel quickly. In equations 2 and 3, we could cancel x if we had opposite signs. So let's do that. But let's also come up with a different pair and cancel the same variable. So again, I saw that in equations 2 and 3, it would be straightforward to eliminate x. And how I'm going to do that is multiply equation 2 by negative 1 and add that to equation 3. I have to do a little more work, though, to get the same variable, x, to eliminate from another pair of equations. I'm going to multiply everything in equation 2 by negative 3 and add it to equation 1. Now, I've just copied these down here. I haven't done the multiplication yet, let alone the addition. You'll see that in a moment. Now, typically, I would focus on one pair at a time, but to speed things up, I have shown the multiplication in both of these. And now I'm going to do the addition so that x will cancel out in both pairs, and I'll have a 2 by 2 system just involving y and z. Okay, I've done the multiplication I said I was going to do, and then I added along the columns, got the x's to cancel here, added up the y's, added up the z's, and added up the constants on the other side of the equal sign. Same thing for the other pair. And now that's going to make up a 2 by 2 system that we already know how to solve. I'll continue with elimination. So I'm going to copy those 2 equations that just have y and z. And I want you to notice that we don't have to multiply by integers. We can multiply by fractions as well. And since I've got everything even on this second equation involving y and z, I'm going to multiply everything in that one by 1/2 in just a moment. You'll see why short. As a matter of fact, let's make that go even a little more quickly. I've got a negative 2 versus a positive 17 in front of z. If I multiplied by 1/2 to equation 5, this is equation 4 right here, this is equation 5. If I multiplied by 1/2, then I'd have a negative 1z. I'd have to multiply again by 17 to get a negative 17. So what I'm going to do is put those two together and multiply equation 5 by 17/2 and add that to equation 4. So far, I'm just concentrating on multiplying equation 5 by 17/2. And what I've done is I've used the fact that every coefficient there was even to reduce, and now I still have to multiply by 17. And here's what I get when I've multiplied by the 17. Again, I divided everything by 2 when I was doing reducing. Now I've multiplied by the 17. So I do have a negative 17z that I can cancel with the negative 17z to cancel with positive 17z up here in equation 4. Granted, we're dealing with some bigger numbers, but I suspect that if I had gone a different route, I could still do it, but the numbers would be even worse. So now I'm going to add that thing that's equivalent to equation 5 and add it to equation 4. Adding the like terms along the columns, I will have negative 90y. The z's will cancel out, and then looks like 450, negative 450 on the right-hand side, which doesn't look so bad because then when I divide both sides by negative 90, I get that y is positive 5. I'm going to go back to one of the equations I had up here, equation 4 or equation 5, and plug in that y equals 5 to find out z. And since the numbers are smaller in equation 5, I'll plug it in there. Doing the multiplication, I will get a negative 40. So I'm going to add that, add a 40 to both sides. And then divide both sides by negative 2 to get that z is positive 1. And now that we have two of the variables, y and z, we can plug those back into one of the original equations and solve for x. And the nicest might be either equation 2 or equation 3. I'm going to go with equation 3. Plug in what we found for y and z and see what we get for x. And I was saying equation 2 or equation 3 because we have a coefficient of 1 there in front of the x. So let's see what happens. Going to have a little bit of multiplication to do. One of those multiplications, though, is 6 times z. 6 times 1, that's 6. And we had a minus sign in front of that. So I'm going to do the other multiplication and combine the like terms on the same side. And then finally add 21 to both sides to get that x equals 8. And here's what we would see as an ordered triple. Then I'm going to follow that up by a check. So again, here's what we would see as an ordered triple. And since I came up with what x is equal to from the third equation, I'm going to do my check in the second and first. It wouldn't hurt to go with the third. So in equations 1 and 2 respectively, here's what we want to check. And doing my multiplication first, I'm going to have 24 minus 35 plus 5. And that would give me negative 11 plus 5, which is equal to negative 6. It checks on the first one. On the second one, 8 plus 25 minus 4 will give me 33 minus 4, which does equal 29. So that checks out. Let's go on to our third example. We'll have one more after that. Okay, so on this third system of equations, it seems like it would be easiest to get either x to cancel by taking equation 3 and multiplying it by a positive 2, adding it to both the first and the second equation. Or maybe I could just add equations 2 and equation 3 to cancel y versus double equation 3 to cancel with y in the first equation. I'm going to go with that second one. All right, I've just copied down each pair. I haven't done any of the multiplication yet, let alone the adding. You'll see the multiplication first and then the adding. Here's the result of multiplying equation 3 by 2, and I'm about ready to add that to equation 1. I don't have to do any multiplication with equations 2 and 3 to get some cancellation. In fact, I've done the addition on the second pair first to get x plus z equals 12. The y's have canceled out. In fact, it's going to turn out that I didn't need to do that, because look over here. The x's, we have 2 and negative 2, negative 4 and positive 4. Those are going to cancel out, giving us that 0 equals 12. And we've talked about how we should interpret that when all the variables drop out, but we're getting unequal numbers. Specifically, we would conclude that the system is inconsistent. There are no solutions to this system. In other words, the solution is the empty set. The empty set. And on this last one, we also have a special situation. If I were to take equation 2 and multiply everything by 4, then I would add up equations 1 and 2 after multiplying by 4 and get all the variables drop out and 0 equals 0. Whereas if I multiply equation 2, everything by negative 3, I'd get negative 3x, which would cancel with this, plus 3y canceling with this, and negative 15z canceling with this, all the variables dropping out. Also multiplying this by negative 3, I'd get negative 21, canceling this out. So with both pairs, I get 0 equaling 0. In this case, we have infinitely many solutions. Here's how that would get expressed on MyLab. I'm not exactly sure why they include this, because it could have been any one of the equations. Really, equations 1 and 3 are multiples of equation 2. So to me, it would have been easier to say, well, once you have a solution to this equation, then those ordered triples that are on that plane would be on these other two planes from equation 1 and equation 3. But if that's true, well, okay, take equation 1. Take an ordered triple that's a solution to equation 1. It's a point on that plane. Then it must be a solution to these other two equations. That's all I've got for now. Hope that helps, and I'll see you in class on Monday.